week I told you that I might be away for the meeting outside, but it turns out that the meeting has been canceled, so I can have a regular class here next week as well. So this is good news, right? Or bad news? So if you remember what we have done yesterday, not yesterday, last week, I think I still need to wake me up. Exponential ijk, exponential pqk, epsilon is delta ip, delta jq, minus delta iq, delta jp. And using this property, you can have A cross B cross C, B C A minus C A B. And I gave you homework that to prove this relationship using both Levi-Civita symbol and the traditional way, right? Using the explicit form of vector product forms is 27 components. You can actually carry out all the calculations, and then you can show this final result. So I'm going to do a little bit more. Let me see what I have planned. To show that, right? We are going to define field. Field is a quantity that depends on both space and time. So there are two kinds of fields. One is called scalar field, such as f, x, y, z, t. So our space-time is four-dimensional. So we have three space dimensions and one time dimension. So we are going to consider the maximum four-dimensional cases. Well, actually, the theoretical physicists think the universe is composed of 11 dimensions. The 10 space dimension with the one time dimension is called string theory, and about 6 of the space dimensions is actually called very tinily, so you cannot see actually each other. But at very high energy, you can actually see the 11 dimensions. That's the theoretical predictions, but we are basically engineers, so you don't have to worry about those sort of minute details. So let's just think about space-time is four-dimensional. The vector field is something like F with a vector. It's a component such that F x, y, z. X is a unit vector in the x direction, and this is called the component in the x direction. X, y, z, t, y, f, y, x, y, z, t, plus z, f, z, x, y, z, t. And we call this as the component of a vector field f in x direction, or x component of a vector field f. It's just notation. And we are also going to consider curve C. Curve is a two-dimensional object or one-dimensional object, and we can define some origin. And let's define some point in curve Q. This is x, y, z. Oh. Thank you. Okay, this is better. Something's hard. What happens? What's happening? X, Y, Z. So P is, let's say, the coordinate of the P is X, Y, Z, and Q is a little displacement of a point from P, so it's X plus delta X, Y plus delta Y, Z plus delta Z. And it's called XR, R plus delta R, and this vector, delta R. So PQ point on the curve C. And this is delta R. And so probably we need a magnifier to look at this. Oh, where should I put? So if we take a closer look at this curve, then this is curve PQ. This is the result of the magnification. So actually this part becomes this. And we have R plus delta R, and this is delta R, and this distance is called ds. So ds is actually distance between P and Q on curve C. And the part of the curve that is related to ds is called arc. And the direct line, delta R, is called chord. So arc is actually from the archer, This is called arch. Who is going to hold this? So archer actually came from the word arc. Chord is actually a necklace. So this is called chord. Chord is a direct line. And arc is like curved line. Then ds or delta s is square root of delta x square, delta y square, delta z square on curve C. So if you want to calculate this dsdr, I guess still you need time to copy. The slide, delta s is defined by the following way, right? So this is delta s. So if you use this definition, R vector is defined as x, y hat, z hat. So dsdr is ds dx x, ds dy y, dz ds dz z. And absolute value of dsdr is dsdr with the square root of this, right? So it turns out that this is ds square dx square, dy square ds square, ds dz square. It's 1 over ds, square root of dx square, dy square, dz square. But previously, we have defined that if I go back to the ds is actually dx square plus dy square plus dz square, right? So it turns out that this ds divided by ds is equal to 1. So dsdr is a unit vector, but also we need to determine the direction of this vector, right? So the mathematics is actually related to the drawing. So we need to draw a lot of pictures or curve or something like that. So can I move on? This is R. This is center of the coordinate. R plus delta R. This is delta R. So this is this. this vector is actually a unit tangent vector at P, x, y, z. And this is curve. So this is a very interesting concept that we need to pursue. And also we like to compare the change of a function between two different coordinates. If we have x, y, z. Let's forget about time function for now. And we like to compare the two results, q minus fp. The change of function from p to q. So f q minus fp is f x plus delta x, y plus delta y, z plus delta z, minus f x, y, z. What is this? Is there any simple expression for expressing this? I would like to introduce you two very important concepts in mathematics. It's called identity. So in mathematics, you can manipulate equations without changing anything by either adding 0 or multiplying by 1. It doesn't change, right? So let's try f x plus delta x y plus delta y, z plus delta z, minus f x, y, z. And see what happens if we add 0. Adding 0 means you subtract something and add the same thing, right? So I can subtract f, x, y, delta y, z plus delta z, and add the same thing, x, y, delta y, z plus delta z. And subtract this. And add. An original expression. So basically this is 0, right? and this is again 0. So far, those two equations are the same, right? I haven't changed anything. By adding 2 zeros, let's have some space. So far, the three expressions are the same, right? This is the original equation, that the function difference of the function between Q and P. And then I added 1 0, another 0, right? So I added 2 zeros, so it doesn't change anything. So this is a final result. And what else? I told you that you can do something without changing anything by multiplying 1, right? So multiplying 1 means divide by something and then multiply by the same thing. So maybe it's different color. I can divide the whole thing by delta x and multiply by delta x. The second line, divide by delta y, multiply by delta y. Third line, delta z, delta z. So what is this for small delta x? If you change the function by tiny amount in x direction by delta x and subtract the original function without adding the delta x and divide by delta x, what does that mean? Partial derivative, right? So if you remember your first year, the freshman calculus class, this is going to be partial x, partial f, right? Likewise, the second expression become partial y, partial f. And third expression, this becomes partial z, partial f. So the whole thing can be written as partial x, partial f, delta x, plus partial y, partial f, delta y, plus partial z, partial f, delta z. So can I move on to the next page? So it turns out that if we have a curve, one point P, another point Q, this is R, R plus delta R, F, Q minus FP, is fx plus delta x, y plus delta y, z plus delta z, minus fx y z turns out to be partial x partial f delta x partial y partial f delta y partial z partial f delta z. And this is very interesting form. We might write this way as an inner product of two different vectors, such as x partial f, y partial f, z partial f, dot x delta x, y delta y, z delta z. And this is nothing but delta r, right? Delta r vector. This can be also written as this way: x partial f, y partial y, z partial z, and f with that delta r. And we call this is looks like a vector. We call this delta. And call del operator. Called del. Del is the vector differential operator. So it looks like we have a curve. This is your origin. This is point P, this is point Q, R, delta R, no. R plus delta R. This is your vector delta R. FP is del F dot delta R. And delta R is actually proportional to tangent vector, right? ds dr. So what would be the condition for the maximum change of this function? If you move from P to Q, what would be the condition for this del operator? So if you have two vectors which is formed by the inner product is proportional to cosine theta, right? The direction of this delta f and direction of this delta r. And this angle between two vectors is cosine theta, right? So when would be the maximum? The maximum of cosine theta is equal to. So what is the maximum of cosine theta? And theta is equal to? Louder? 0, right? So maximum occurs when theta is equal to 0. So the maximum change of fq minus fp occurs when grade delta f is parallel to delta r, or tangent to the curve, right? So maximum change of function along the curve occurs when this del f, whatever called, is proposed parallel to the tangent vector, right? And we call this del f gradient of f. So we are going to spend some time to actually carry out the calculation of del f. Let me see if I'm forgetting anything. Maximum change of this. Okay. I think I didn't forget anything. I brought it back to note just in case if I forget something. Yeah, I don't need this. So let's do some practice. Examples. Say f x, y, z. So let's try to calculate gradient f. So according to the definition, this is x, partial f, right? Plus y, partial f, plus z, partial f. So this is x, partial, x, y, z, y, partial, x, y, z, partial, x, y, z. So this is called x. So what is this? If we differentiate x, y, z by x, what do you get? Just y, z, right? How about this? So partial derivative means you just think y and partial derivative by x means you just consider y and z as constant. So this is xz, and this is xy. So you will get x, y, z plus y, x, c plus z, x, y. How about f x, y, z is r, square root of x square plus y square plus z square. So in this case, how do you calculate? The first case is easier, but this case is a bit difficult, right? So this is actually a composite function. So say g, x, y, z, x square plus y square plus z square, then this is square root of g, x, y, z, right? So how do you calculate this? Partial x, partial square root of g, x, y, z. Anybody remembers chain rule that you probably have learned during the freshman year calculus? Chain rule. If you remember chain rule, raise your hand. Right? Probably if you have taken my class in the spring semester, also you must have learned that. But just in case, assuming that you forget everything, let's start from the beginning. So I'm going to spend a little more time on chain rule and then continue this discussion. And am I loud enough? Can you hear me well? So I was afraid that wearing mask actually make my voice funny and unrecognizable, but it turns out to be it's okay, right? So assuming that f is a function of g, x, y, z, but let's start with a simple case. Start with a simpler case. Assuming that f is a gx. And you like to calculate what is dx, dfx. According to the definition of derivative, is defined as some small delta goes to 0. You have delta f g x plus delta minus f gx. That's the original definition of the derivative, right? You try to find a small change of function with delta and then divide by delta, right? That's the definition of the first of the derivative. And say g x plus delta can be written as g x plus delta g as well. So if x is changing by a small delta, then gx also may be changing by a small delta g, right? It's a small change of delta. Of g. Then you can write down the whole thing as the following way. Delta goes by deltas, f g delta g minus f g. Also, delta G goes to 0 as delta goes to 0, right? Because delta G is a small change of G. When delta goes to 0, then delta G also must be goes to 0. Must be going to 0. So we can write down this without changing anything. Delta goes to 0, or delta G goes to 0 as well. And you first divide by delta G, f G plus delta G minus f G. But by dividing by delta G and multiplying by delta G is equal to 1, right? So you haven't changed anything. So if we divide by the first expression by delta G, and then multiply by delta G, then this is equal to 1, right? So you haven't changed anything. So this becomes dg df dx dg. So we have a chain rule that dx df gx is dg df dx dg, and this is called chain rule. And so if you go back to your freshman calculus class, I think most likely you have learned this. Also in my class in the spring semester as well. And then we can extend this to the partial derivative case. So can I move on? And if I'm going too fast, don't worry about that. You can always go back to YouTube, so you can check back. So beautiful chain rule. dx df gx dg df dx dg. This is first case. If we have a partial x, partial f gx y z, then dg df partial f partial g. Likewise, partial y partial f gx y z, dg df partial y partial g, partial z partial f g x y z, dg df partial z partial g. So you can check as a homework. And maybe you can take a 5 minutes break before I proceed. So let's do some practice. So we have defined r as square root of x squared plus y squared plus z squared as g, x, y, z. So g is x squared plus y squared plus z squared. So partial x, partial r would be dg dr partial x partial g. So this part is easy, right? So this is partial x squared plus y squared plus z squared. And the definition of partial derivative is when you take a partial derivative by x, you ignore y and z as a constant, right? So basically, if you differentiate x squared by x, what do you get? You have x squared, and you derivative of x squared by x, what do you get? 2x, right? This is basically high school calculus. 수학의 정석, right? Just in case you forgot your high school math, let's just do simple review. So dx dx squared is simply you take the limit, delta goes to 0, delta x plus delta square minus x square, right? Delta goes to 0. X square. You know how to do x square, right? 2 del x delta x plus delta x square minus x square. So this cancels each other. Delta goes to 0. 2x plus delta x, 2x. Just in case you forgot your high school calculus. So now you know if you differentiate x squared by x, you get 2x, right? Square root of x is a little bit more difficult. So I'm going to spend some time from the scratch just in case to refresh your memory. Square root. So small delta is approximate to 1 plus 1/2 delta. You can check. Is that? So this becomes delta over square root of x 1 plus delta over x 1/2 minus square root of x is This is actually how Newton has arrived this result in about 300 years ago. If you cannot trust me, you can actually do anybody's calculator. And then you can calculate this number, like a square root of 1 plus 0.1. Anybody's calculator? What is that? One point 0.449 something, right? So anybody has a calculator? You just need to remember if you can calculate 1 plus delta 1 over n is approximately 1 over delta over n. So it's very neat if you remember this formula. So there is another way, actually. This is, I'm using approximation, but this is correct expression, actually, right? So if you compare these two different approaches, you can get right. So I told you the simpler way, but there is another way. Just do nothing. How do you do nothing? So basically, this is equal to 1, right? So you divide by whole thing by root x plus delta plus square root of x and multiplied by square root of x delta plus delta. This is called rationalization, 유리화. Then we have this delta times the So what happened to the denominator? This is simply x plus delta minus x, right? This is called denominator. Denominator. In Korean, denominator means 분자, denominator means 분모. And the whole thing is called a fraction. This whole thing is called a fraction. 분수. So, this is more exact way. We have delta, delta, and this cancels each other, and then you get basically 2 square root of x, right? So if you go back, also square root of 1 plus delta is 1 plus delta over 2. So this is the same expression, right? So I think I'm spending too much time on these things that you're supposed to know already, but just in case. So let's go back to the partial x partial square root of r. This is partial x partial x squared plus y squared plus z squared, and we call this is g. So this is tg dr. Oh, sorry, this is not square root of r. This is r. And partial x partial g. So this is 2 square root of g and 2x, right? And square root of g is simply r over x. So same thing goes for likewise partial y partial r is y over r, partial r partial z c over r. So gradient of r is x over r, y over r, z over r. Eventually, we like to need time to copy. Eventually, calculate this. Oh, how about gradient of fr? This is x partial fr, y partial fr, z partial fr. So that means x dl df partial x partial r, y, you can apply the chain rule again, partial y partial r, z dl df partial z partial r. So we have x over r dl df y y over r dl df z over r dl df. So one good example is when f of r is 1 over r. What is r over r? In high school, you might have memorized, right? Minus 1 over r squared, right? Let's just double check. So dr dfr, delta goes down, delta fr plus delta one over delta r plus delta minus 1 over r one over delta r plus delta r minus r plus delta. So this r cancels this delta cancels this, you get minus r squared, right? So in high school, you probably just memorize this. But now you can actually derive. And once you have derived, you can still memorize. You don't have to do every time from the first principle. So in many things, it may be better for you to memorize after you have derived yourself. So this is a very important relationship in the gravitation and electromagnetic theory, actually. For example, if you have a charge Q, and if you want to calculate the potential at R, then you have a potential which is 4 pi epsilon 0 R over Q. An electric field is defined by minus of gradient of VR. So minus of 4 pi epsilon square over charge Q, this is charge. Gradient of 1 over R is R square over 4 pi epsilon 0 R square Q X over R over Y R over ZZ. Or any force. Force can be calculated by taking the gradient, negative gradient. So about half of you are taking electromagnetic theory, right? So you probably are learning this alongside with my math class. So that's about gradient. if you have a vector field f x partial x y partial y z partial z x y z, then you can make an inner product with the der operator, der f, which is x partial y partial z partial z dot x fx y fy z fz. This is becoming partial x partial fx partial y partial fy xy z partial z partial fc xyz. It does have a name called divergence. Divergence of, we call this divergence of f. For example, divergence of R x partial y partial z partial xx yy zz. So this is basically partial x partial y partial z 3. The divergence of R is simply 3. Divergence is a special place in electromagnetic theory as well. So in electromagnetic theory, we call electric field H magnetic field, B as a magnetic flux, T as electric flux, or called density. Then divergence of B is always 0. And divergence of D is rho. It's called charge density. What's Let's just stop here and then check. So both gradient and divergence are closely related to the electromagnetic theory that we actually learning electromagnetic theory in part as well as an example. So there are four different components for the electric field. H is called the magnetic field, D is called the magnetic flux, or sometimes magnetic flux density, G is called the electric flux density. And divergence of B is always zero. And divergence of D is charge density, related to charge density. And we are going to cover one more vector quantity, vector differential operator quantity called the curl. So can I move on? Remember how to calculate the vector product. It's x, ay, bz minus az, by, y, az, bx minus ax, bz plus z, ax, by minus ay, bz. It's actually, the rule is easy to remember that x, y, z, you have a counterclockwise, you have plus, clockwise, minus. So using this rule, x, y, z is plus always. Y, z, x is always plus. Z, x, y is always positive. And if you change the order, you got negative. So, likewise, del plus a or f. You can obtain the same thing. Del z, f, del y, z, minus del z, f, y, plus y, del z, fx, del x, fz, z, del x, fy, del y, fx. Of course, here del x is partial x, del y is partial y, del z partial z. So you can write down here x partial y partial fz minus partial z partial fy, y partial z partial fx minus partial x partial fz plus z partial x partial fy minus partial y partial fx. And it has a name called curl. So far we have learned three different vector operations: gradient, divergence, and curl. So gradient gives actually maximum change of a scalar function. Divergence and curl has different implications, and we are going to cover that maybe in the future, but not right now. The importance of this divergence and curl is also from the Maxwell's equations and electromagnetic theory. So example, so I'm going to cover the electromagnetic field as an example, so you can actually benefit when you take another class, right? EM. Is Professor Juan Lee is teaching the class? Or I don't know who is teaching the electromagnetic class. Here. Again, EM. And this mu is a special name called permeability. This epsilon has a permittivity. And this whole thing is called Maxwell's equation. And Maxwell's equation has been formulated about mid-19th century, 18 something. The first equation is very important. It's called Faraday's law. So Faraday's law says changing the magnetic flux produces electric field. This is related to the generation of electricity, electric current, or electricity. Very important, because current civilization relies on everything electric current, right? Electricity. Assuming that we don't have electricity, what will happen? I have to teach you in front of, with many candles, not with the screen, right? If we still don't have electric current or electricity, then it's like a 19th century, early 19th century cultures. Then we don't have all this civilization, handphone, iPad. It's not possible, right? So two things has happened in the history, actually three. So if I a bit divert from my class, the first event was Newton's law, F equal ma. So Newton's law actually allowed steam engine in 1735. Anybody remembers the name of the inventor of steam engine? James Watt, right? 1735. James Watt. So we are using watt as a unit of energy, power, right? So this actually led to the Industrial Revolution in 17th and 18th century. Second event in technology is Maxwell's equation. Mid-19th century. That led to the electricity and also the Maxwell's eventual discovery of Maxwell's equation is electromagnetic wave. You can make electromagnetic wave propagate in 1894. Hertz discovered that actually you can produce the electromagnetic wave and you can detect it over the distance. So two things. So electricity with the electromagnetic wave constitute the modern technology, right? Information technology. Led to electricity, vacuum tube, transistors, and so on. So those Maxwell's equations are actually basis of IT. So everything started from 19th century, that the modern IT technology is based on this whole vector differential equation. And so that's why you are learning vector analysis. It's important, very important, cornerstone of a modern technology. And another third one is still going on, is quantum mechanics. So classical mechanics and electromagnetic theory concern the macroscopic world. Beginning of 20th century, that in some cases, like when you're investigating atoms or very tiny object, then the classical mechanics or electromagnetic theory is no longer valid. So in those domains, this domain of quantum mechanics in 20th century. And in the last 20 years, those are applied to quantum computation. This is another so quantum computation can be the basis of the third industrial revolution in the next 100 years. So first thing, we are based on classical mechanics. That's to the industrial revolution of modern industry. And secondly, at the end of the 19th century, with the discovery of Maxwell's equation, led to the modern IT technology. And early 20th century, discovery of quantum mechanics is still going on, maybe led to another industrial revolution based on quantum computation. So that's one thing that can be starting from the math. Maybe we can take a break for 5 minutes. Can continue. Assuming that we have a vector field which is x squared in the x direction, y squared in the y direction, and z squared in z direction. And let's try to calculate this chord of f. X partial y partial fz minus partial z f y y partial z partial fx partial x partial fz partial x partial fy partial y partial fx. So fz is z squared, right? If we take a derivative of z squared by y, what do you get? If we differentiate the z squared by y, 0, right? So first term is 0. How about second one? Fy is y squared. If we differentiate y squared by z, you get, again, 0. This is a very simple example. Fx is x squared. If we differentiate by x squared by z, you get 0. And fz is z squared. If we differentiate by x, 0. Very good. Same goes for that. Fy is y squared. If we differentiate by x, you get 0. And x is x squared. If we differentiate x squared by y, you still get 0. This is a 0. This is one example. The important thing is you get familiar with the vector operations. So maybe you can do one more example. Okay, this time I will try to make a bit more x, y, z, x, 2, x, y squared z, y, x, y, z squared, z. Maybe x squared. Again, chord f x partial y partial f z minus partial z partial f y y partial z partial f x partial x partial f z plus z partial x partial fy minus partial y partial fx. Now partial this x, y, z square, and if you differentiate by y, what do you get? xz square. Fy is xy square z, and if you differentiate by z, what do you get? Minus 2xy square, and minus minus sign cancels each other, 2xc, right? No, xy square. Y fx is x square yz. If you differentiate by z, you get x square y minus fz xy z square. So if you differentiate by x, you get minus yz square z square. So it can be non-zero. Partial y, this by x, minus 2xc, no, y square z, right? Minus x square yz by y, x square z. So in general, this is non-zero. Just for practice. This might have more meaning. Call divergence of f So let's say this is f, then this is fx, fy, fc, right? So you can say x component partial y partial fc minus partial z partial fy plus y component partial z partial fx minus partial x partial fz plus z component partial x partial fy partial y partial fx. Correct? So partial y partial, what is fc in this case? This, right? Partial z partial f, partial z partial, big fy is partial f partial y. F minus partial x partial z partial f z component partial x partial y partial f partial x, partial f. So this is basically x, partial z, partial square f, minus partial z, partial y, partial square f, partial z, partial x, partial square f, minus partial x, partial z, partial square f, c, partial x, partial y, partial square f, partial y, partial x, partial square f. So in the second order derivative, if you change the order, it doesn't change, right? So this is basically 0. So this cancels each other, and this cancels each other, this, so it becomes 0. So we have a very important relationship that curl times gradient of f is always 0. This is very important result. Just one more topic to cover before we finish. Maybe it's time to copy. Okay. Curl f. We have A cross B cross C, B, C, A, C, A, B. But you have to be careful in applying this vector operation. So we have gradient of divergence of f minus this is called the Laplacian. So I'll give you homework to check this. Or maybe you can, maybe I can just do that. I'll give you homework, but here, right? This. This is x called partial, y partial fz minus partial z partial fx, right? Plus y partial z partial fx minus partial x partial fz, z partial x partial fy partial y partial fx. I will do the hard way first and then do the simpler way. So let's call this as, say, this is y. See, right? So call f x component. Let's just do the x component first. Partial y, partial, call f z component, right? Minus partial z, partial, call f y component. No, x y, z. This must be y. So partial y, partial, z component is this. Partial x, partial fy, minus partial y, partial fx, minus partial z, partial y component is partial z, partial fx, minus partial z, partial fc. This is partial y, partial x, partial fy, minus partial y square, partial fx, minus partial z square, partial square, fx, minus, let me see, this is y component, zx, xz. So it must be minus z square partial fx plus partial z partial x partial fx. So it becomes partial x partial y partial fy plus partial z partial x partial fx minus partial y square partial square fx plus partial z square partial square fx, right? Something is missing. C. It must be C. Let me double check. Even I'm confusing sometimes. So x component is partial y for fz minus z y, right? X, Y, Z, Z, Y. So Z component must be X, Fy minus Yx. Y component must be Z, Fx minus less what's wrong? Partial x. So partial y, partial x. This must be z, right? So let's see. So let's see. Correct? So we have partial x partial y partial fy plus partial z partial fz minus fx partial z square partial square fx. There's still something missing, but we can add 0. So I can add partial x square fx minus partial x square fx. So this is basically 0, right? So that means we have partial x partial x partial fx partial y partial fy partial z partial fz. And maybe I can add this minus partial x square plus partial y square partial z square fx. And this is nothing but divergence of f, right? And this is Laplacian, because Laplacian is partial x square partial y square partial z square partial. Okay, so maybe I can spare some time, here, that core f is same as partial x partial divergence of f minus Laplacian of fx. This is x component. So as I will give you homework to actually calculate. Still need time to copy. Too complicated, right? I just use one page to cover everything. Likewise, y component will be partial y partial C component will be partial Z, partial FC. So actually this is homework. You can check. I mean, you can do the same thing as what I have done for X component, right? So even though I have just done one page, actually it probably needs 3 pages for each. And maybe 20 minutes or so for each cases. So if we combine them together, what do we get? Is X component of partial Y partial divergence of F minus XFX plus Y component of partial Y partial C component is basically just gradient of this, right? Minus F. So this relationship is actually the same as this. Correct? Another maybe easier way is just to use this. I component another homework. Check this. So you will get the same result. Okay, so what do you think about me stopping here today? A bit early, but you must be hungry, right? Okay, so see you next week. And, 2 weeks from now, we are going to have a first quiz. September 28th, 1 hour quiz, 1.5 hour quiz. And then you can prepare 1-page cheating sheet. One-page cheating sheet. Cheating sheet is a cunning paper, so you are allowed to bring 1-page cheating sheet for quiz. And the topic of the quiz will be whatever we cover next week, up to next week. 1.5 hours. And after the class, after the quiz, we are going to continue with the class. 1 hour to 1.5. I haven't decided with how long, but so end of this month, September 28th, Wednesday, we are going to have 1 to 1.5 hour quiz about topics from the beginning to whatever we are going to cover next week. And then you are allowed to bring 1 page cheating sheet. Funding paper, 1 page. A4 size, one-sided. And there are websites, I don't know which one is. Ask my student, my TA, for previous quiz problems. There were, I think, archives of previous quiz problems. Okay? So if you have questions, you can also ask me next week as well about the quiz.